Back in 1982, the Cosmos Alpha probe, a marvel of engineering, penetrated the caustic, sulfuric acid atmosphere and touched down on the surface of the most hostile planet in our solar system, Venus. The pressure there is enough to buckle a deep-sea submersible, the temperature is hot enough to liquefy lead, and the sky is perpetually cloaked in acid-saturated clouds. Despite this hellish environment, Cosmos Alpha held on for a record-breaking 127 minutes, sending back images and invaluable data before the crushing pressure and searing heat finally claimed it. That probe was engineered to endure any terrestrial disaster, but Venus presented a challenge far beyond what our scientists had ever conceived. Now picture me, a lone human, suddenly materializing on the surface of that infernal world. How long could I possibly last? What would be the first thing to kill me? Let's embark on this hypothetical journey. If I were to appear on Venus's surface without any form of protection, I wouldn't even have a moment to witness my surroundings. My end would be nearly instantaneous, and it wouldn't be the scorching heat or the corrosive acid that got me first. The colossal atmospheric pressure would be the immediate executioner. The pressure on Venus is equivalent to being submerged nearly a kilometer deep in the ocean. This immense weight would instantly implode my body. However, let's make it a fair fight. Imagine I'm outfitted in a spacesuit constructed with the same robust technology as the Cosmos Alpha probe. In that scenario, my journey on Venus begins. The first thing I'd register is the oppressive, dense yellow-orange haze enveloping me. This is the result of a thick atmosphere dominated by carbon dioxide and clouds of sulfuric acid, which scatters sunlight and casts the entire planet in a permanent, eerie twilight. But the dim light is hardly a concern, as there's little to see, just desolate plains of volcanic rock, littered with fissures and stones. My spacesuit is fortified with durable titanium plates, engineered to withstand 90 atmospheres of pressure. This reinforcement adds significant mass, and I'd feel every bit of it since Venus's gravity is only about 10% less than Earth's, making the difference almost imperceptible. The thermal regulation system of my suit has to be the most sophisticated design imaginable, and for a very good reason. Venus holds the title of the hottest planet in our solar system, with surface temperatures reaching a staggering 470 degrees Celsius. What's worse is that this heat is inescapable, persisting even on the planet's dark side. This is a direct consequence of a runaway greenhouse effect. Sunlight penetrates the atmosphere and warms the planet, but the dense blanket of gases traps the heat, turning the world into a planetary furnace. Just like the Cosmos Alpha probe, my suit needs to be a fortress against this heat. My spacesuit is shielded by a multi-layered thermal barrier, with an external layer composed of silicon carbide, capable of enduring temperatures up to 500 degrees Celsius. The internal cooling mechanism works by evaporating specialized liquids, which absorb the intense heat and channel it away from my body. I push forward, my movements a struggle, but fueled by a determined confidence as I traverse the scorching, rocky terrain. It's so hot here that common metals like tin, zinc, and lead exist only as puddles of molten liquid. The poisonous sulfuric acid relentlessly assaults my suit, but for the moment, it holds firm, thanks to its titanium structure coated with chemically inert materials like tantalum and gold, which provide a robust defense against corrosion. All around me, the carbon dioxide exists in a supercritical state. At 90 bars of pressure, it's no longer merely a gas, but a strange, dense fluid that behaves like something between a gas and a liquid, a medium that would obliterate any known life form in an instant. After a short while, my physical condition starts to degrade. The cooling system is the first component to give out. No matter how advanced, it simply cannot cope with such relentless, extreme temperatures. My suit begins to overheat rapidly from the inside. With no escape from the ambient heat, heat stroke is instantaneous. I lose consciousness, and within a minute, the internal temperature soars to critical levels, and I perish. Simultaneously, the chemical shielding of my suit starts to fail. The aggressive sulfuric acid, combined with the crushing pressure, begins to compromise its integrity. The structure heats up, develops microfractures, and finally collapses under the hellish conditions of Venus. I managed to survive for a whole 20 minutes on this planet, an impressive accomplishment considering it's the most scorching world in the solar system. For comparison, in a standard ASIA-issued spacesuit, I wouldn't have lasted even a single second. But what about the other planets? What kind of gear would I need to survive their environments, and which one poses the greatest danger? My next destination is the planet closest to the Sun and also the smallest in the solar system, Mercury. My fate here hinges entirely on where I choose to land, on the frigid dark side or the sun-blasted day side. The primary challenge on Mercury is its near-total lack of an atmosphere, which means there's no mechanism for heat distribution. Consequently, its surface temperatures experience more dramatic fluctuations than any other planet in our solar system, plummeting to -173 degrees Celsius at night and soaring to 427 degrees Celsius during the day. Despite this, I dare to step onto its cold, dark surface. My heavy-duty suit shields me from the freezing void, but the first sensation is the profound icy chill radiating from the ground beneath my feet. Without an atmosphere to act as a medium, heat transfer is minimal. The first thing I notice is how closely the landscape mirrors our moon. The surface is a desolate panorama of craters, cracks, and fine dust, a monochrome world of grays where the only light comes from the faint glimmer of distant stars. Dressed in my ultra-protective thermal and anti-radiation gear, I can manage a brief walk across Mercury's dark side. However, waiting for the sun to rise would be a fatal error. When the sun does crest the horizon, I see that it looks nothing like it does from Earth. Instead of its familiar, warm, yellowish glow, it shines with a blinding, pure white intensity. This is because Mercury has no atmosphere to scatter and soften its light. Furthermore, from this proximity, the sun appears 3 times larger and is overwhelmingly brighter than it is from our home planet. The temperature climbs with alarming speed, and without the most advanced protection, my suit would be unable to shield me from the lethal onslaught of radiation. Ultraviolet rays would inflict severe burns within minutes if no shielding were in place. Fortunately, my suit is radiation-proof. However, even the most sophisticated cooling systems can't maintain a safe internal temperature for long under the direct heat of the Mercurian sun. The temperature inside my suit inevitably climbs, fast approaching critical levels. There is nowhere to seek shelter, and waiting for nightfall is futile. Once the sun has risen, darkness will not return for another 29 Earth days. Within minutes, intense solar radiation penetrates my suit's electronic systems, disabling nearly all life support functions. Soon after, my internal organs begin absorbing lethal doses of radiation and start to fail. Even with an intact oxygen supply, my cooling system has completely shut down. I quickly lose consciousness and collapse onto the burning surface of Mercury. Here I lasted only 15 minutes. The combination of intense radiation and extreme temperatures left me with no chance of survival. But perhaps my next destination will be more forgiving. Maybe I'll not only get to walk its surface but even have a chance to stay for good. My next stop is Mars. I've landed near the planet's equator, not far from the site where the American Space Exploration Administration's Endeavour rover touched down. The landscape feels both familiar and alien, reminiscent of Earth's desert regions, but bathed in an unusual atmosphere. The sky has a pale butterscotch hue. The plains around me are scattered with rocks and boulders of all sizes. I'm fortunate to have arrived on a summer day in the Martian mid-latitudes, where temperatures at the equator can reach a comfortable 20 degrees Celsius. For now, my suit's thermal regulation system is on standby. However, it will become critical as night approaches, when temperatures are expected to plummet to a frigid -70 degrees Celsius. Despite my heavy suit, moving around here is relatively easy. Mars's gravity is about 2.5 times weaker than Earth's, which means I weigh 2.5 times less. The temperature might be tolerable for now, but I must remain constantly aware of the high levels of radiation, which are over 20 times higher than on Earth. During solar flare events, this radiation level spikes dramatically, as Mars lacks a global magnetic field and a dense atmosphere to provide protection. Thankfully, my suit is reinforced with multiple layers of advanced polymer composites to mitigate these risks. I've now spent several hours on the red planet without facing any serious issues. It almost seems like nothing is stopping me from setting up camp and constructing a small underground shelter. However, recent data shows that Martian soil contains high concentrations of perchlorates, toxic compounds that could pose a long-term health risk and complicate agriculture. The longer I remain on Mars, the more its low gravity and intense radiation will weaken my body. This dangerous combination will slowly degrade my cardiovascular system and even impair cognitive function over time. After 10 hours on Mars, my oxygen supply is depleted. I successfully return to my spacecraft and leave the red planet behind. But my next destination is truly a different beast. I'm heading toward a gas giant, the largest planet in our solar system. Reaching Jupiter and surviving is an incredibly daunting task. As I approach the colossal planet, I encounter extreme levels of radiation, higher than anywhere else in the solar system aside from the sun itself. This is due to Jupiter's immense magnetic field, which extends 7 million kilometers toward the sun and stretches nearly to Saturn's orbit in the opposite direction. This field, 18,000 times stronger than Earth's, traps enormous amounts of solar radiation within its magnetosphere. Only the thick titanium hull of my spacecraft can shield me from its lethal effects. Let's assume I've managed to reach my destination. Now, I must descend into Jupiter's atmosphere. Fortunately, thanks to ASIA's Daedalus probe, which plunged into Jupiter's clouds in 1995, I have some idea of what to expect. The Daedalus probe descended 87 miles into Jupiter's atmosphere before it ceased to function. Its descent lasted 58 minutes, a remarkable survival time under such extreme conditions. Now I must attempt to replicate this feat. My spacesuit is uniquely designed to withstand intense radiation. Like Daedalus, its outer shell is made of a titanium alloy, hermetically sealed with polyethylene and advanced composites to reflect radiation. To counteract the immense pressure, the suit has a multi-layered shock-absorbing system that distributes force evenly. Finally, I make the leap, plunging toward Jupiter. The first thing I encounter is a layer of ammonia clouds, located 12 miles above the planet's theoretical surface. The temperature here is below -100 degrees Celsius. Though it's unimaginably cold, my suit is equipped with powerful thermal insulation, and I quickly fall past this freezing layer. Within a minute, the temperatures begin to rise, and the atmospheric pressure approaches that of Earth. I'm nearing what could be considered Jupiter's surface, but what awaits me next are catastrophic winds reaching speeds of 370 miles per hour, which hurl me into a massive, swirling vortex. My suit holds, but my body cannot withstand the immense G-forces and I do not survive. Even then, the ferocious winds and massive lightning strikes, some spanning over 600 miles, fail to destroy my suit, so it continues its descent. With every passing mile, the temperature and pressure intensify. Within minutes, my lifeless body, encased in its suit, reaches the water cloud layer, where temperatures hover around 0 degrees Celsius. In another 2 minutes, I descend to a depth of 87 miles, where the temperature has climbed to 150 degrees Celsius, and the pressure is 24 bars. This is the same depth where the Daedalus probe stopped transmitting. Well, I lasted only 3 minutes since entering Jupiter's atmosphere, which is honestly far too little time to witness anything extraordinary. However, had I chosen one of Jupiter's most fascinating moons, Europa, my fate might have been different. This time, I stand firmly on solid ground. Beneath my feet lies a thick ice crust, 9 to 15 miles deep, concealing a vast ocean of liquid water. The temperature here is a staggering -150 degrees Celsius, which is almost as cold as Mercury's dark side. I find myself on an endless, frozen wasteland, roughly the size of Earth's moon. Its smooth surface is scarred by a network of countless cracks. There is no atmosphere to speak of, and the radiation streaming from Jupiter is extreme. My suit protects me, but not for long. Due to Europa's weak gravity, my weight is 7.5 times less than on Earth, allowing me to move effortlessly despite my heavy gear. In the distance, I spot a massive geyser spewing water vapor 120 miles into the vacuum of space. The ice beneath my feet trembles and I collapse. It wasn't an earthquake. The intense radiation has disabled my suit's oxygen supply system. My vision darkens, dizziness sets in, and I soon lose consciousness. Ironically, Europa has plenty of oxygen. Its surface generates about 26 pounds of it per second as Jupiter's radiation splits water molecules. But I won't be able to breathe it. Soon, the radiation completely destroys my suit. I survived for 15 minutes on Europa, the same amount of time I endured on Mercury. Now, a different gas giant awaits. Through the spaceship's viewport, I see a planet I instantly recognize by its magnificent rings. I'm approaching Saturn. Just like with Jupiter, landing on the planet itself is impossible. But my curiosity gets the better of me, and once again, I'm ready to take the risk. Donning a massive spacesuit with reinforced radiation protection, I prepare for the jump. Already in the upper layers of the atmosphere, I'm greeted by a familiar sight, an aurora, similar to Earth's northern lights. It appears due to the interaction of the planet's magnetic field with charged particles from the sun. Surprisingly, my instruments are still functioning, and my descent continues. After some time I enter the troposphere, the lower atmospheric layer of Saturn, which stretches for 150 miles. Here, the weather conditions unleash their full power. Hurricanes and winds reach speeds of 1,300 feet per second, many times stronger than Earth's most destructive storms. It is in this layer that the reason for Saturn's yellowish appearance from space becomes clear. The answer lies in dense clouds composed of ammonia crystals. Even the slightest breach in my suit in this toxic environment would be instantly fatal. Near Saturn's hypothetical surface, temperatures drop to -200 degrees Celsius. This extreme cold immediately coats my suit in a layer of ice, and my electronic devices begin to fail. It seems like the end. Darkness surrounds me, since hardly any sunlight penetrates to this depth. Before long, the increasing pressure starts to deform my suit. With each passing moment, breathing becomes harder, until the crushing force finally destroys my protection. I perish. I managed to survive for 5 minutes while falling into Saturn, slightly longer than on Jupiter. But just like Jupiter, Saturn has a much more promising candidate for a landing. Its moon, Titan. It is the only satellite in the solar system with a dense atmosphere. Stepping onto its surface, the thought that I'm no longer endlessly falling into a gas giant is a comforting one. It truly warms my soul. Figuratively, of course, since Titan's ambient temperature is a relatively mild -180 degrees Celsius. To ensure my survival, my spacesuit is covered in highly reflective materials that effectively repel the cold. Inside, it's lined with silica aerogel, an exceptional insulator that blocks extreme temperatures and maintains thermal stability. However, visibility here is poor due to an atmosphere rich in organic compounds, which casts everything in a yellowish haze. This opaque sky prevents me from seeing Saturn or other celestial bodies. But moving on Titan is relatively easy, since its gravity is about 1/7 of Earth's. Even in a heavy suit, I feel comfortable. The atmospheric pressure here is also manageable, about 1.5 times greater than Earth's. After some time, I discover a small lake, resembling those on Earth. But I don't even think about touching it. Instead of water, it's a mixture of liquid methane and ethane. What exists as a gas on Earth is a liquid here due to the frigid temperatures. I've now been on Titan for over an hour. The radiation levels are higher than on Earth, but my suit continues to shield me, allowing me to explore. However, soon, I start to shiver as an extreme cold creeps into my body. My suit's thermal protection is finally failing against Titan's -180 degrees Celsius environment. Half an hour later, I lose consciousness and collapse onto the icy surface, succumbing to hypothermia. I survived here for 2.5 hours. We can all agree that's much better than a few minutes of falling into Saturn's abyss. Titan turned out to be an extremely cold world, but how would I fare on the coldest planet in the solar system? To find out, we head to Uranus. Looking at the serene, bluish-green planet, I realize another plunge into a gas giant awaits me. However, this experience is unlikely to be much different from the previous ones. The probability of dying here from winds reaching 560 miles per hour is extremely high. And if I somehow survived that, the temperature of minus 220 degrees Celsius would surely finish me off. No thermal protection can save you from that. At best, my fall will last 3 to 5 minutes before my inevitable death. A more interesting option is to visit Uranus's moons. First on the list is Titania, the planet's largest satellite with a radius of just 490 miles, about half the size of our own moon. If I weigh 175 pounds on Earth, I'd weigh only about 4.5 pounds on Titania. With my suit, the total weight would be around 9 pounds. But if I choose to land on Miranda, Uranus's smallest major moon with a radius of just 146 miles, I'd have to be careful not to accidentally drift off into space. My total weight, including the suit, would be just over 2 pounds. After experiencing near weightlessness on this tiny moon, I decide to move on. Up next is a journey to the planet that only one spacecraft has ever visited, Odyssey 2. At first glance, Neptune appears as a peaceful blue orb, seemingly harmless. But in reality, it's a true nightmare. It harbors a deadly mix of factors: temperatures below minus 220 degrees Celsius, an atmosphere composed of hydrogen, helium, and methane, and the strongest winds in the solar system, reaching speeds of 1,300 miles per hour, 5 times the speed of sound. And then there's the radiation, which, while weaker than on Saturn or Jupiter, is still potent enough to damage my suit and harm me. As soon as I enter the upper atmosphere, I find myself in a lethal zone of intense radiation and violent storms. My existence on Neptune is fleeting, just 2 minutes of free fall before I hit an area of such intense radiation and wind that death is instantaneous regardless of how advanced my suit is. But there's still one destination left: Pluto, the dwarf planet, and the final challenge in our planetary survival gauntlet. The diameter of this dwarf planet is just 1,480 miles, which is smaller than our moon, which measures 2,160 miles across. Yet despite its small size and low mass, Pluto has a thin but present atmosphere, offering slight protection from cosmic radiation. However, the radiation here is still abundant. Stepping onto Pluto's surface, my first task is to turn on my flashlight. Darkness reigns supreme here. Looking up, I spot the sun, now resembling just a particularly bright star. Its light takes over 5 hours to reach this distant world. The gravity is similar to that of the moon, so my heavy suit won't be a problem. What I should be worried about is the temperature, which plunges to minus 220 degrees Celsius. Exploring the surface, I observe a stark landscape of water ice and gray-brown rock. Pluto appears like a frozen desert, with hills and valleys reminiscent of Mercury's dark side. After just a few minutes, the extreme cold begins to degrade the materials of my suit, making them brittle. A sudden catastrophic breach occurs, and I perish instantly. My time on this icy world lasted only 8 minutes, marking the end of my planetary survival challenge. Liam Donovan, the visionary CEO of Ares Aeronautics, is convinced that we won't survive as a species without colonizing other planets. Exploration of extraterrestrial worlds will allow us to survive a possible apocalypse, and also give us access to vast natural resources. He believes the starting point should be Mars. The head of Ares Aeronautics predicts that human beings will first set foot on Mars by 2031, and, within a few years after that, the first Martian colonies could start popping up around the planet. And while preparation for the upcoming missions is in full swing, including successful test flights of the new Starhopper vehicle, Mars remains a tricky place. Take dust, for example. Because of the intensity of the winds, dust would constantly accumulate on solar panels, putting them out of operation. The tiny sharp rocks that dot the planet's surface could be even more damaging. In 2022, ASIA showed images of the Endeavour rover's tires being torn to shreds by the Martian terrain. In fact, Mars is quite hostile. It's very cold, with an average surface temperature of about -60 degrees Celsius. A person there would quickly turn into an ice cube without some kind of protection or spacesuit. The magnetic field on the planet is very weak, and the atmosphere is 100 times thinner than Earth's, meaning there's no protection from cosmic radiation. In addition, there's nothing to breathe because the atmosphere of Mars is a poisonous cocktail of carbon dioxide, nitrogen, and argon gases. But with the help of modern technology, all of this can be addressed. Even the gravity, which is almost 3 times less than that on Earth, won't bring much trouble, although it will be necessary to spend several hours a day on special exercise machines to stay in good shape. Liam Donovan is already preparing for humans to land on the Red Planet, but the flight will be very long. The average distance between Earth and Mars is 225 million kilometers. The best time for space flights to Mars from Earth comes once every 2 years, when the 2 planets' orbits are the closest. This is when the most advanced Starhopper spacecraft would launch from Earth. Each ship will be attached to a reusable carrier rocket with 42 powerful vortex engines. The total height of the rocket is 122 meters, the largest ever built, even surpassing ASIA's Saturn V lunar rocket. The booster rocket will accelerate the spacecraft to a speed of 8,650 kilometers per hour, then detach and return to Earth. The ship will deliver people to Mars in about 7 months. After filling its tanks with fuel made on Mars, the ship can be launched back to Earth using its own engines. To supply the rockets with fuel, a plant will be built on Mars to produce methane and liquid oxygen from water ice and atmospheric carbon dioxide. The spacecraft will carry 100 or even 200 people and 100 tons of cargo. The Starhopper flotilla will make about 1,000 voyages a year, according to Donovan. At this rate, by 2050, a city with millions of citizens and a developed industry could appear on the Red Planet. So, the idea is to build a city under protective domes. The dwellings will actually be built by robots before people arrive, and, the rest could be printed by settlers using 3-dimensional printers. ASIA has already held a competition for the best Martian house design in a special program called the 3D Printed Habitat Challenge. First place went to the Ares Ice Shelter Project, which is a 4-story structure adapted to the conditions of Mars. It has like many apartments and public rooms connected by a spiral staircase. The rooms would have curved walls to create the illusion of more space. But whatever shape the houses on Mars take, Liam Donovan believes that the most important thing is to make the settlement independent of suppliers from Earth. Food would be grown on hydroponic farms powered by solar energy. As for the Martian soil, it's still unclear whether Earth plants will take root there. Recently, lunar soil has been tested in the same regard. If there are settlers on the moon, they'll need to at least partially provide themselves with food. To find out if this would work, scientists from ASIA and the University of Florida sowed green crops in lunar regolith and volcanic ash and added a nutrient solution. Arabidopsis thaliana, a relative of cruciferous vegetables, sprouted perfectly in this mixture. And this raised the moon's ranking as a site for colonization. Still, our satellite is too small to become a second Earth. Scientists are considering all the planets in the solar system that could become a full-fledged replacement for our home, even Mercury. It's difficult to imagine that a new Earth would be a celestial body that rotates so close to the Sun. Our star heats Mercury's surface to an average of 179 degrees Celsius, and the daily maximum temperature gets even higher, up to 427 degrees Celsius, and it has no atmosphere to deflect solar radiation. A solution to this was proposed back in 2011. The MESSENGER probe spotted a ton of hollows on the surface of Mercury, which could indicate the presence of underground lava tubes. Colonies built inside such tubes would be naturally protected from solar radiation and extreme temperatures. But the lack of gravity is still a major issue. The absence of gravity deprives human muscles of their usual load, and they begin to atrophy quite fast. And our bones would suffer even more in prolonged weightlessness. For example, bone mass first decreases, then due to lack of stress on the bones, calcium starts to break down and is released into the bloodstream, increasing the chance of bone fracture. So because the blood pressure in the human brain is much lower than in our feet, if you take gravity away, it would stabilize equally all across the body. This could lead to bleeding in blood vessels, impaired vision, and honestly, even a stroke. But in case we decide to relocate to Venus, we'll avoid such troubles. The planet's gravity is almost equal to Earth's. Venus has a dense atmosphere that could shelter colonists from radiation. In addition, there's a huge amount of carbon dioxide accumulated in the atmosphere of the planet, and actually, oxygen can be extracted from it. But there's a problem. Behind Venus's thick veil lies a living hell. Large quantities of carbon dioxide in the atmosphere create an extreme greenhouse effect and raise the temperature to about 475 degrees Celsius. The atmospheric pressure on Venus is about the same as the pressure at a depth of 900 meters underwater on Earth, so even the most protected probes would only survive for a few hours there before being flattened by the gigantic atmospheric pressure. The planet's upper atmosphere is also flooded with poisonous acid rain, many times more corrosive than the most acidic rain on our planet. And the wind, at a speed of 360 kilometers per hour, blows away everything in its path. So why are scientists still considering colonizing such a horrible planet? It turns out that Venus hides a place like Earth. At an altitude of about 50 kilometers, there's a region with a level of pressure and gravity almost like that found on Earth, and the temperature there is about 30 to 50 degrees Celsius. So building floating habitats above the planet's clouds might be a good idea. The ASEA team has already begun developing the High-Altitude Planetary Explorer, or HAPE, concept. The initial mission envisaged an airship 129 meters long and 34 meters high, protected from high temperatures with only a thin outer layer. One idea was to use a nitrogen and oxygen mixture as a lifting gas for the airship, making its full volume habitable. It would make the airship lighter than the Venusian atmosphere, allowing it to float above the clouds. And because Venus is close to the sun, there would be abundant solar energy, meaning no problems with energy to power the floating habitats and cool the airship. But at the edge of the solar system is yet another great place for colonists. Although this celestial body is Saturn's satellite, Titan is the size of a small planet and is the 10th largest object in the solar system, including the Sun. Its diameter is just over 1 times that of Mercury, nearly 1.5 times that of the Moon, and about 2/5 that of Earth. The giant satellite resembles our planet more than any other celestial body in the solar system. Titan has many lakes of liquid methane and ethane, which are strikingly similar to Earth's bodies of water. They're constantly replenished by methane rains. The land is covered with dunes of solid hydrocarbons that look, pretty similar to the sand dunes we have on Earth. These hydrocarbons could actually be an excellent source of energy for the colonists. Even there, on this distant world, humans would have shields against radiation. Saturn's magnetosphere and Titan's nitrogen atmosphere, which is about 50% thicker than Earth's, provide protection. And the water ice just beneath the surface of the satellite can be used to produce oxygen. And Titan is, terribly cold. Temperatures average about minus 180 degrees Celsius. But colonists don't have to hide from the bitter cold under a spacesuit. Titan's dense atmosphere dissipates the cold, which could allow people to walk around wearing warm clothes and respirators. And, they could make housing out of plastic using local raw materials. Scientists believe that on Titan we should build houses in the form of domes inflated with warm oxygen and nitrogen. Another unique feature about Titan is that the first people there could actually fly like birds. So the weak gravity, combined with a dense atmosphere, would actually allow you to perform stunts in the air with wings attached to your back. But do we actually need another celestial body to live on? The idea of colonizing space isn't really new. It was actually proposed way back in the 1970s. But recently, a team from MIT developed a project for a modern settlement among the stars and planets. It's designed in the form of a torus, with a diameter of 1.6 kilometers and a thickness of 150 meters. Such a dwelling would be able to accommodate 10,000 people. So, it would need to rotate continuously around its axis to create artificial gravity. And there would be an industrial area for processing ore from nearby planets and their satellites. The leftover slag could be dumped outside and, it would actually become a reliable shield against all types of radiation. In the living area, each colonist would be given a separate apartment located on different levels. All of them would be connected by spiral staircases where, honestly, people would often see each other upside down. This effect would occur as a result of the constant rotation of the structure. If you enjoyed this planetary survival challenge, support this video with a like and, of course, subscribe to our channel for more deep dives into the cosmos.